Okay, so hydrogen bonding is what we come to next. First of all, before there's any confusion, I just want to make it clear that when we talk about hydrogen bonding, we are talking about an intermolecular attraction. We are not talking about a type of chemical bond. So hydrogen bonding occurs between molecules, not within a molecule. I really wish that they had chosen a better name for hydrogen bonding, because it really does make it sound like it's a regular chemical bond, but it really isn't. It's more of a hydrogen attraction between molecules. Okay, having said that, hydrogen bonding is possible whenever you have a polar molecule that has hydrogen bonded directly to small electronegative atoms, specifically nitrogen, oxygen, or fluorine. So you need to have hydrogen bonded directly to nitrogen, oxygen, or fluorine. Now, it's important to remember this because it's quite common to have hydrogen and nitrogen or hydrogen and oxygen in the same molecule together, but they have to be bonded directly to each other before you will actually experience hydrogen bonding between the molecules of that compound. So some examples of the types of compounds that can do hydrogen bonding. First of all, water. Hydrogen bonding is responsible for a lot of the important characteristics of water, like first and foremost, the fact that it's a liquid at room temperature and not a gas. Given its small size and small molar mass, by all rights, water should be a gas at room temperature. Other molecules of similar size and similar molar mass are gases at room temperature, even ones that are polar. But actually, it's the addition of hydrogen bonds on top of the dipole-dipole attractions that allows water to condense into a liquid and to be a liquid at room temperature. If it didn't have hydrogen bonds, then water would be a gas at room temperature. Also, alcohols, like methanol. Methanol has a structure like so, where 3 of the 4 hydrogens are bonded directly to the carbon, but the 4th hydrogen is bonded directly to the oxygen. And that right there is what allows hydrogen bonding. And that actually is why alcohols dissolve so well in water. It's the fact that alcohols can hydrogen bond with water. If it were just a case of trying to dissolve alcohols in water because alcohols are polar and water is polar, without the hydrogen bonds, alcohols would dissolve in water, but they would not be miscible in all proportions like they are. So hydrogen bonding increases the solubility of alcohols in water a lot. Ammonia has hydrogen directly bonded to nitrogen. And so ammonia is very soluble in water because it can hydrogen bond with the water molecules. And hydrogen fluoride or hydrofluoric acid is also a compound that can hydrogen bond. Okay, so hydrogen bonding acts between the same atoms that dipole-dipole attractions act between. So essentially, hydrogen bonding augments dipole-dipole attractions. Essentially, it makes the dipole-dipole attractions even stronger than they otherwise would be. The way it does this is that the high electronegativity of the nitrogen, oxygen, or fluorine draws extra electron density away from the hydrogen. And hydrogen has a relatively low electronegativity for nonmetals. And so the nitrogen, oxygen, fluorine are able to draw an extra amount of electron density away from the hydrogen. And that makes the hydrogen's partial positive charge bigger. And also the partial negative charge of the nitrogen, oxygen, or fluorine also bigger. And the result is an attraction between bigger positive charge and a bigger negative charge. And according to Coulomb's law, that's a stronger attraction. Okay, and so that strengthens the attraction between the partial positive charge on one molecule and the partial negative on another molecule. Also, because hydrogen is small and nitrogen, oxygen, and fluorine are small, as well as very electronegative, their smallness allows them to get close to each other. And that, again, getting close increases the strength of the attraction. So it's this augmentation of the dipole attraction that is known as the hydrogen bond. Okay, the hydrogen bond is actually stronger than the dipole-dipole attraction and augments it. And compounds that can engage in hydrogen bonding have unusually high melting points and boiling points for their molar masses. And that's because the particles are so strongly attracted to one another, it takes a lot of energy to get them apart. And so the hydrogen bonds, as I mentioned, form in the same places between molecules, even between the same atoms, as the dipole attractions do. And so you have water molecules, and you have the dipole-dipole attraction between the partially positive hydrogen of one water molecule and the partially negative oxygen of another. But that's basically along the same lines. that is also a hydrogen bonding attraction. And that goes on as sort of a network throughout the entire body of the water. And you can actually look at H2O, as we've seen, engages not only in dipole-dipole attractions, but also in hydrogen bonding, and that's a liquid at room temperature. H2S, which is a similar compound, only involving sulfur as the central atom instead of oxygen, but sulfur is directly below oxygen in the periodic table, so it tends to form compounds with the same formula and the same geometry as oxygen does. And it turns out, though, that H2S, even though it's quite a bit heavier than H2O, is a gas at room temperature. And the difference is the lack of hydrogen bonding in H2S. So water manages to be a liquid even though it's quite a bit lighter than H2S. H2S is as a gas even though it's quite a bit heavier because it can't engage in hydrogen bonding. So that makes all the difference. And one other type of attraction we have and actually, before we move on, I'll just say, there is a practice question that we can answer here. The question is, which of these two compounds will have a higher boiling point and why? HCl or HF? And of the two of them, if we didn't know about hydrogen bonding, we would choose HCl because HCl is heavier. Chlorine is below fluorine in the periodic table. So HCl is quite a bit heavier than HF. But HF can engage in hydrogen bonding and HCl can't. And so the answer is HF because of the hydrogen bonding. So HF, even though it's lighter than HCl, it has a higher boiling point because it can engage in hydrogen bonding. Okay, so that can have a big effect. All right, ion dipole attractions. This is the strongest intermolecular attractions of all. Because ions have full positive or negative charges. None of this, partial charge nonsense. You're going to have a full +1 or +2 or +3 or -1, -2, -3 charge on an ion. And they can be attracted to positive charges that are opposite in sign. These attractions will be pretty strong because you may only have a partial charge on one side, but you've got a full charge on the other side. And an example of this would be something that we already mentioned when we were talking about solubility. That is how ionic compounds dissolve in water through hydration by water molecules. So for example, for sodium chloride, you'll have an Na plus ion and a Cl minus ion. And in order to get them to dissolve in water, you first of all, of course, have to overcome the attraction between the Na plus and the Cl minus. And you have to overcome the attraction between the H2O molecules, their attractions for each other. And part of the way that you can compensate for overcoming those attractions is by establishing new attractions between the H2Os and the ions. If the ion is positively charged, like sodium is, then the H2Os will gather around the sodium ions with the partial negative charged side of the water molecule facing the positive ion. And the water molecules will gather around the chloride ion with the partial positive hydrogen ends of the molecules facing the chloride ion. And by gathering around the ions like this, the water molecules can stabilize the charges on the ions, basically cancel the charges out, so that the Na plus ion, that positive charge on the Na plus ion, is basically canceled out by several partial negative charges gathering around it, and that leaves the sodium ion then free to move around in the water. And the same in reverse for the chloride ions. The minus charge on the chloride is stabilized by all those partial positive hydrogens gathering around it, and that leaves the chloride ion free to move around in the water. And so these are ion dipole attractions. All right, so that is the strongest intermolecular attraction of all. And you find that when you have ionic compounds in the presence of polar compounds, like, for instance, dissolving an ionic compound in water. Some of the consequences of intermolecular attractions are things like surface tension, viscosity, and capillary action, and so that's what we're going to look at next. Surface tension is the tendency of molecules at the surface of a liquid to stick to each other in a way that essentially excludes outside objects from entering the liquid, or at least resists it, if not actually excluding. Viscosity has to do with resistance to flowing or pouring in a liquid due to the strength of the attractions between particles in a liquid. And capillary action has to do with the ability of liquids to flow in glass tubes because of the attraction of the liquids for the glass of the tube versus their attractions for each other. So let's take those one at a time, though, because it can get a little confusing otherwise. So first of all, surface tension. Particles in a liquid will be attracted to each other, and those attractions tend to go in all directions. But when you have particles at the surface, they experience attractions differently from particles on the interior of the substance, because there's one entire side at the surface where the particles don't have any neighbors. And that is The result of that is surface tension. One of the most noticeable effects of surface tension is that it allows objects more dense than a liquid to float on top of the liquid, as long as they don't penetrate the surface. That is, if the mass is sufficiently spread out. This is something that any number of bugs that can walk on water take advantage of. And the mass of the bug is spread out over all 6 of its legs, and they usually have relatively large feet too, which can sort of steady themselves at the surface of the water without actually poking through the surface. And the tendency of the molecules at the surface of the water to stick to each other has the effect of making it relatively difficult for outside objects to penetrate that surface. You can even take a steel, well, the book uses the example of a steel paper clip. You can also do it with something like a steel sewing needle. You can actually float it on the surface of water as long as you ease it onto the water from the side, basically lying flat. So if you fill up a glass of water right to the brim so that the water is about to go cascading over the side of the glass and sort of ease the needle onto the surface of the water from the side, then you can actually get a steel needle to float on top of the water, even though the steel obviously is a lot more dense than the water. If, though, you try inserting that needle onto the surface of the water point first, then obviously all of that weight is going to be pressing down on that little tiny point, and the point is going to penetrate the surface and the needle will sink immediately. But if you sort of ease it on from the side and where the weight is more spread out, then you can actually get it to float. Also, while you're doing that, you might notice that when you fill the glass up to the very brim, you can actually keep adding water for a bit, and the water itself kind of bulges up over the rim of the glass without actually spilling over. And that itself is a consequence of the surface tension of water. So if you have a surface of a glass, you can actually fill up the water so that it kind of looks like that. And it doesn't actually spill over yet. If you add some more, eventually it'll spill over. But the fact that you can get the water to go up above the surface or the rim of the glass a little bit is a tribute to water's ability to stick to itself because of its strong intermolecular attractions. Not only dispersion forces, but dipole-dipole forces and hydrogen bonds as well. And those 3 things together make water very attracted to itself. So surface tension is defined as the tendency of liquids to minimize their surface area. Or you can, in colloquial terms, you can think of it as basically the tendency of liquid molecules to stick together. Different liquids have different levels of surface tension. Some liquids have very little surface tension. Other liquids have a lot. So something like, say, water or motor oil will have a lot of surface tension, whereas something like, say, alcohol or gasoline have very little surface tension. The reason that they do this is that the molecules at the surface interact with fewer neighbors than those in the interior do. Okay, so because down inside the body of the liquid, you've got basically molecules on all sides of any particular molecule, above and below and to the left and to the right and in front and behind. When you get to the surface, you've still got molecules below and to the left and to the right and in front and back, but there's nothing above. And so they have fewer molecules to interact with at the surface than they do down in the interior. Because of this, molecules at the surface have higher potential energy. And they're less stable. Basically, the molecules want to be on the interior because that would give them lower potential energy. Okay, it's because they'll be more stable down in the interior. And so what they do is they minimize the surface area because that lowers the potential energy. Because it essentially minimizes the number of atoms or molecules at the surface, which are the ones with the high potential energy. Reduce the number of molecules with high potential energy, you reduce the potential energy overall. And some views of this, they refer to the surface actually contracting in order to minimize the surface area. So another definition of surface tension is the energy required to increase the surface area of a liquid by a given amount. The given amount usually being 1 unit of area, which in the SI system would normally be a meter. So the units of surface tension would normally be units of energy over units of area. The SI units would be joules per square meter. And at room temperature, surface tension of water would be 72.8 millijoules per square meter. Or 0.0728 joules per meter. or square meter. It's the tendency to minimize the surface area that makes the surface harder to penetrate. Versus moving around in the interior. And it's basically like sometimes the analogy is used to forming a sort of skin on the top of the water. Sort of like how pudding left out for a while forms kind of a skin on top of it. And the skin is a little bit tougher than the pudding underneath. It's kind of the same idea with surface tension in water. It forms sort of a skin almost on top of the water. And in order to penetrate the surface with an object, the surface area has to increase slightly which requires energy. All right. The surface tension is generally larger for stronger intermolecular forces. A good example is water. Water has relatively high surface tension. And water has dispersion forces. Dipole-dipole attractions. And hydrogen bonding. Something like acetone, nail polish remover, has low surface tension. And that's because it has dispersion force attractions and dipole-dipole, but no hydrogen bonding. Something like gasoline has very low surface tension. And that's because gasoline is actually a mixture of several different types of molecules. But one thing almost all of them have in common is that they're non-polar. So that means that they have dispersion force attractions only. There may be a few molecules here and there that are somewhat polar, but generally a vast majority of them are nonpolar. So that would mean dispersion only. And that means very little attraction between the molecules. So it means very low surface tension. You cannot float a needle on gasoline or a paper clip. Bugs that can walk on water with no problem would not be able to walk on gasoline, even if they really wanted to. And things like that. It has other consequences too. Lack of surface or lack of intermolecular attractions between the molecules that make up, say, gasoline, are also responsible for gasoline's relatively low boiling point compared to water, and its relatively low density compared to water, and so on and so on and so on. Generally speaking, also, oh, and one other thing is that it has intermolecular attractions also have to do with how easily liquids spill. If you've ever tried carrying gasoline in an open container, you probably know what I mean. You can barely move that stuff without having it spill all over the place. Whereas water, is pretty stable. You can actually do a lot of very outlandish stuff with water without spilling it, but not with gasoline. Okay, higher surface tension usually means that droplets are more likely to be spherical. That is, they're spherical as long as gravity is not having a big effect on their shape. And that's because spheres have a minimum amount of surface area relative to their volume among all of the geometric shapes. And that's why water droplets tend to be more or less spherical. It would be funny if, say, like a pyramid shape had the smallest surface area relative to volume, then water droplets would be pyramid shaped. But it's not. The sphere has the minimal surface area. And choosing a shape that has the minimal surface area relative to volume has the effect of minimizing the number of molecules at the surface and maximizing the number in the interior. Okay, and so that's a little review of surface tension. We're well over 30 minutes again, so I'm going to have to stop it there, and next time we'll go on to viscosity.